All right, the problem we have today involves an intramolecular transesterification, if that's a mouthful. Intramolecular transesterification. All right. This was one of the challenge problems from the book, but I really liked it, so I threw it at you guys pretty early on.
I liked it too.
All right, let's see if my pen will start working here. There we go. All right. What do you guys think the first step is? That's pretty similar from last chapter. Protonate the ester in this case. The ester carbonyl oxygen. And so I'm just going to draw this as catalytic H+. So first step, we're going to protonate the ketone. All right, so now we've turned that carbonyl into an excellent electrophile. What do you guys think the next step is? Exactly. So there's a lot of side conversations. Let's make sure everyone can hear. Once we prime that ester and make it much more electrophilic, it's much more prone to a nucleophilic attack. So in this case, we've got a nucleophile on our parent molecule. So this will add in. Oh. So now we get this fused bicyclic system. And it looks a little bit like that. You can draw it three-dimensionally if you want to, but it's a little bit strained. And then you also have this oxygen that's protonated. The next step involves a proton transfer, and I'm drawing it with alcohol. And why do you think I'm drawing it with alcohol? So if we're taking this reaction and our reagent is neat, meaning no solvent, and we put in a drop of sulfuric acid, it can act as its own solvent, right? So assuming you have some unreacted molecule around, the alcohol group on that can facilitate a proton transfer. So in this case, I'm going to avoid using the conjugate anion because that's a really poor base. The alcohol is actually a better base than the conjugate base of sulfuric acid. Nope. In this case, I didn't say it was dilute.
But I'm just saying if it was, like, you don't have to say how much you're doing. Just for clarification.
This way we avoid negative charges. There we go. And now we've also got our protonated alcohol that I said can facilitate in that proton transfer. And then we can protonate this other side. Oh. Got OH, protonated the ether. All right, what do you guys think the next step is?
Push down the lone pair from the alcohol?
Exactly, so we do a malicious shove, kind of like we saw before. Nope. And now we've got a ester with a positive charge on it. And then in the last step, we can show deprotonation. I'll just show that as minus H plus and regenerate our catalytic acid. And so this would be called an intramolecular transesterification.
a notation question.
Yep.
What do brackets signify?
In this
Like
case,
abbreviated process, or are they?
in this case, we can never have just a proton floating around, so it's indicating loss of a proton. And so I put brackets around it. If you see brackets above a reaction arrow like that, that's usually indication that it's catalytic.
That's what I.
Exactly. So in this reaction, all you do is you have your starting material, you put in a drop of acid, and then all of a sudden you get this equilibrium of two different products. And sometimes this is unexpected and surprises people, but you can rationalize it by showing the trans-esterification and arrow pushing. No. I'm not entirely sure why they call it trans, because all it means is you're substituting one ester for another ester. Yeah. All right, so let's continue on to chapter 21 and move on to acid chlorides. Yep.
So when I was doing some book coding, some of the nomenclature was like really intense. You're not going to be like that, right?
I want you guys to know the basic nomenclature. In the ACS exam, if you go through the practice test, you'll see example naming questions. They stick, for the most part, to the basics.
Okay, and another thing I noticed is they have the IU path name and common name. For the ones that you gave us with specific names, we just need to know those ones?
Yep, the ones I've given you in lecture, you should know.
Okay, so we don't need to know the IU path name for those? Or-
No.
Okay. Which you can figure out again.
All right, so in order to make acid chlorides, we're going to use a reagent we've seen before. Does anybody remember how we convert alcohols into chlorines? Thionyl chloride, exactly. So in this reaction, we use SOCl2 in order to convert the alcohol on our carboxylic acid into a chloride. And then in this reaction, if you remember back to our alcohol section, we create sulfur dioxide, and we also produce hydrochloric acid. So let's go over the mechanism for this, because it is slightly different than the one for alcohols. Yeah, you generally do this with some sort of non-nucleophilic base, and we'll talk about that especially when we get into the next sections. Occasionally you see it done without base too, if you're just forming the acid. Okay, so we've got our alcohol, and we've got thionyl chloride. Thionyl chloride is one of the world's best electrophiles, so it really, really wants electrons. And so what happens is that this lone pair will jump down, this lone pair will jump up, and you push electrons onto those sulfurs. So the carbonyl lone pair is what's attacking the sulfur. Oop, let me move this a bit. There we go. So now we've, negative. Now we've got a Zwitter ion where the oxygen has a negative charge coming off of the sulfur. We've got really good leaving groups on here, right? We can knock off a chlorine and eliminate that negative charge. So this will come down, kick off our chlorine. Reform our double bond to sulfur. We still have our positive charge there. In this case, we can show a chlorine coming and grabbing the proton off. Alternatively, you could show any sort of base coming and grabbing that if you do have a base around. In fact, let me just change this to a B. And now we've got our neutral species. which is ready to go. So what we can do now is we can have the chloride that got ejected actually add in and it can kick up electrons. So now we've got a chlorine, got an oxygen with a negative charge, got an oxygen, got sulfur, and a chlorine. This is an amazing leaving group. In fact, normally you would want to push the lone pair down from the oxygen and kick off the chlorine, but in this case it outcompetes that. And we kick electrons over here. Now we end up with our acid chloride. Plus our oxygen with the negative charge. And now, if you remember from the alcohol section, this can clamp down and kick off our chlorine. And when we do that, the reason why this reaction is so favorable is that you form sulfur dioxide gas plus your chloride salt. So essentially we're trying to make a better leaving group than the halogen in order to get the halogen to install. There are a few other reagents that are used for this transformation, but for our book, they tend to stick with thionyl chloride. You can also use PCl5, and we're not going to get into that mechanism. All right, so now let's go into reactions of carboxylic acids. They're kind of the granddaddy of them all because they're very, very reactive. They can be turned into a ton of different functional groups. Yep, we're going to get a mind map going on at the end too, just to kind of organize our thoughts. The first one is that if you take an acid chloride and you react it with water, what do you think it'll go to? Yeah, it'll just go back to the carboxylic acid. And you'll make HCl during this. Let's just briefly show the mechanism. I'm not going to show it for the next ones because they're all so similar. But if you've got your acid chloride and you've got water, your water can add in to the carbonyl. It's a very, very good electrophile, so you don't have to protonate it first. In this case, I'm showing it as a one-way arrow because the overall reaction is strongly, strongly favoring formation of the carboxylic acid.
If you use a specialty, you add a lot of hydrochloric acid to a carboxylic acid with form?
No.
No?
No, the carboxylic acid is thermodynamically much, much more stable. All right, the next step, you can clamp down, kick off your halide. You have your chloride that can act as a weak base. And you get straight back to your carboxylic acid. So the question is, why am I showing you this? Well, you can't do any reactions that involve water with acid chlorides unless you're purposely trying to go back to your carboxylic acid. Occasionally what people do is they go through all this effort of making their acid chloride, and then they forget that it's water sensitive, and they do a reaction that involves water as a solvent. Acid chlorides are shipped in airtight bottles. That way they don't even react in the moisture with the moisture in the air. They're very, very sensitive reagents. There's also one other thing, too, I wanted to point out. That this reaction produces a strong acid. And oftentimes this is very undesirable. In this case, the strong acid can be trapped by adding a base. And specifically, we want to add a non-nucleophilic base. Specifically, the most common one that's used is this guy, which is pyridine. What happens if we use a nucleophilic base? Yeah, it'll just substitute in place of the water. So if we use a strong nucleophile, we'll get nucleophilic acyl substitution. So if we are going to use a base, it has to be a base that's non-nucleophilic. All right, let's go into the next reaction that's a little bit more useful but closely related to hydrolysis. This is alcoholysis. It sounds like a disease.
Yeah.
Got a bad case of alcoholysis. Couldn't wake up on Saturday morning until about 11. All right, so we've got our acid chloride. We can add in an alcohol. These are normally done in pyridine. And if you do this, you can interconvert all the way to an ester. And then your byproduct, which is much more gentle, is pyridinium chloride. So if you use pyridine as your base, it will end up deprotonating during the mechanism, and you'll form the pyridinium salt. Pyridinium salts aren't nearly as acidic as hydrochloric acid, and this is much easier and more gentle. So if we have a carboxylic acid, now we've got a method to turn it into an acid chloride and then convert it into an ester. It's possible to go from your carboxylic acid to the ester in one step, but sometimes you have to do this depending on your reaction. You guys saw in lab that you can go directly from a carboxylic acid to an ester by doing addition of a strong acid and skip the intermediate step. We'll talk about that when we get into esters. All right, the next one. Is if we use amines instead of alcohols. Same principle applies. This time we don't have to use pyridine. And why is that? Oh, it is a base too, right? So it's a base and a nucleophile, so it can not only do the nucleophilic attack, but it can also do the deprotonation. So if we do this, we can convert from an acid chloride to an amide. And we get ammonium chloride as our salt. If we want to make things a little bit more substituted, we can use an acid chloride. And we can use a primary amine. And you can get your conjugate salt out. And if you want to make your fully substituted amine, you're just going to use a secondary amine. Oops, this one should be an NH3 up here. And there we go. So we can interconvert between acid chlorides to a bunch of different amides. This is how people used to make peptides. We actually have reagents that are much easier to use now. And if we get time during our section on proteins and peptides, we're going to cover those reagents in more detail. But this is a very rudimentary way of making amide bonds. All right, so those ones are pretty straightforward and easy. Let's go to one that is also a review and one new one. What reagent do you think we can use to get interconvert between an acid chloride and an alcohol? What was that? I thought I heard it.
Right?
Yeah. LAH, right? So it's a carboxylic acid derivative. We can reduce it. So the first step is we'll use LAH,
Water.
and that's in excess. And then second step, we want water. So this is a two-step reaction. And so let's take a look at the mechanism again really quickly for a review. If we've got our acid chloride, the lithium aluminum hydride will kind of sneak up underneath. And the hydride will get added into our acid chloride, kick electrons up. And then the oxygen can kick electrons down, eject off a chlorine. And you end up with an aldehyde. The problem is with these reactions is it's very, very, very hard to stop at the aldehyde. Because if there's any lithium aluminum hydride around, it will just continue reacting. It isn't a reaction where you can control it by adding in a stoichiometric amount of lithium aluminum hydride. Why doesn't it kick back down and shove off a hydrogen?
Hydride's a bad leaving group.
Yeah, hydride's a bad leaving group. So in this case, it can't go in the reverse reaction. But what we can do is react this with an alcohol or with water. And we can get all the way to our primary alcohol. All right, so the cool thing about this is chemists thought about this and they said, well, what if we want to stop at the aldehyde? What are some strategies we can do? What do you guys think?
Don't use LAH.
So we could switch to a different reagent, maybe something that's not as strong of a hydride donor. So we can change the strength. What's another thing we can do? What if we just bulk it up? If it's really, really bulky, it's going to have a hard time approaching and it will slow the reaction down considerably. So what they found was that's actually a great strategy. And we can use a really, really bulky hydride source to get around this. I'll show you guys the behemoth that most people use. It has one hydride off of it. It's got 4 oxygens coming off of it, and each of these oxygens has a tert-butyl group attached onto it. So it can deliver a hydride to the very reactive acid halide. Because it is so reactive, it'll figure out a way to do that. But because it's so bulky, it won't reduce aldehydes. It will only reduce acid halides. So this one has a pretty long name. And it's lithium tri-tert-butoxy aluminum hydride. And so this is used if you want to stop at the aldehyde.
That just abbreviated as LTAH.
What's that?
Is that abbreviated as LTAH?
No, I'll show you guys how it's abbreviated. So if we want aluminum hydride, yeah. So if we have our acid chloride and we want to go to our aldehyde, the way they abbreviate this in your book is they do Li, Al, OR, so that R is some sort of bulky group. And we've got 3 of them, and then we've got a hydride.
There's no easier way for that one.
No, that's how it's abbreviated in your book.
But if we put LTAH,
No, I would not know what you're talking about. So this is a nifty tool. It will not go on to the alcohol. I'll just put an X through there. And then not observed. All right, so let's continue on a little bit. We've got one more set of reactions for acid chlorides. And the next set involve reactions with organometallic reagents. Oh. Reagents. All right, what's our most common organometallic reagent that we've been using? Where we have a metal covalently bound to a carbon. What's that? Not quite. How do we get a really strong carbon nucleophile? A Grignard reagent. So the most common one that we've seen is with Grignard reagents. So if we do this, typically what we see is we can add in one Grignard reagent. And it's very, very hard to stop at the ketone. The next thing that happens is a second equivalent of your Grignard will add in. And then last but not least, we can protonate it. So this is kind of a problem. It's hard to control. So if you do this, you'll get a poor yield of your ketone. So on paper it looks nice, but in practice the Grignard reagents are just too powerful. Kind of like with lithium aluminum hydride, it's just too powerful, it doesn't know when to stop. So to get around it, we use a different organometallic reagent. And the organometallic reagent that we're going to use this time is a new one. So we can still start with our acid chloride. And so what this is called is a lithium dialkyl cuprate. And this will stop at the ketone. So let's take a look at what a lithium dialkyl cuprate looks like. They're really easy to make. All you need is an alkyl halide, and you throw in copper and lithium, and it will form a lithium dialkyl cuprate. We don't need to know the mechanism for this, but you should remember that when you react it with a ketone, or with a man, I can't talk. When you react it with an acid chloride, it will stop at the ketone. All right, so now let's get our map going on here.
I got a whole page for this, huh? Yeah?
If you want.
Should I do it horizontal or vertical? Like a map, like a real map?
So what we're going to do is we're going to put this smack in the center, and we're going to say, all right, we can have our acid chloride. And the first reaction we saw was making it from a carboxylic acid. So if we're trying to go in this direction, what reagent do we need? From our carboxylic acid to our acid chloride. Thionyl chloride.
Oh, come green.
Okay, so SOCl2. What if we want to go in the reverse direction? Water. All right, so that's one portion of our map. What if we want to... Sorry. That's why I put it in the middle. What if you want to go to your ester? What can we add? We need a nucleophile to add in and displace the chloride. So which nucleophile? Yeah, an alcohol, right? And we need pyridine as our base to deprotonate. Okay, so we can convert between those two. We could also interconvert between the ester and the carboxylic acid, but I'll leave that for when we get into the ester section. What about if we want to go back, we have to first go to the carboxylic acid and then back. Yeah. But what, let's just actually draw on this arrow.
Yeah. Let's do it.
How do you think we can go between our ester back to our carboxylic acid? So one thing you can do that's kind of classic, you react it with hydroxide, the strong base, followed by acid. So that's called saponification. So when we get into our soap making lab, we're actually going to do this. You can take long fatty acids or esters, cleave them back to their carboxylic acid. So hydroxide in this case is your nucleophile, and then we add acid in the end to reprotonate our carboxylate. All right. What if we want to make an amide, specifically an amide with two hydrogens coming off of it? Yep, ammonia, right? And specifically, we need two equivalents. All right. Let me actually move this guy. There we go. Yeah, right. We can do the same thing if we want a substituted amide, but in this case we use RNH2. Again, 2 equivalents. We can substitute it even more if we want. And use a secondary amine. Two equivalents. You can't unless you hydrolyze it back to the carboxylic acid. And we'll cover reactions of amides and all of these functional groups as we go along. What about if we want to go to a primary alcohol? We're going to be reducing it, LAH. Followed by H2O. All right. What if we want to go to our aldehyde? It's not LTH. All right, I'm going to do this diagonally. LiAlOR3H followed by H2O. And that's a really big, bulky hydride source that will stop at the aldehyde. All right, what if we want to go to our tertiary alcohol? Grignard, right? Because the Grignard will add in uncontrollably. Let me move this over. Well, in this case, you do need 2 equivalents at least.
So if you had 1 equivalent, could you stop with ketone?
No, you get a mixture. So I'll say 2 equivalents just to be specific. If you add in 1 equivalent, you'll get a mixture of your ketone and your tertiary alcohol, and your yield will be poor of both. It's just too difficult to control.
The last arrow.
Yep, last arrow. All right, so we've got our ketone. What reagents would we need? R2CuLi.
LDC.
Sorry, this is lithium dialkyl cuprate. Let me slide it over a bit. R2CuLi. Okay. So that's pretty much the new toolbox we've acquired today. It looks pretty overwhelming, but the mechanisms are very, very repetitive. If you are struggling with some of the mechanisms, just be careful to double check your arrow pushing and make sure that you're not kicking off a hydride or alcohol. You want to make sure you're pushing off neutral groups or a chloride.
For those last 4 that we just did, is there a mechanism going backwards?
No. Yeah. All right, so now before we head out, I wanted to briefly talk about a side thing.
Me too.
We will actually be able to leave a little bit early.
You're right. We better write this on the calendar. Say it on the calendar.
It's brief, very brief. All right, let's say we've got our acid chloride versus our acid bromide. Which one's more reactive?
Chloride.
So there's some debate. Which one's the better leaving group? No? Bromo, right? So in this case, these are more reactive. And because they're more reactive, people actually avoid making them because they're incredibly unstable. And so a lot of people ask me, well, why don't we see acid bromides very often? Wouldn't they even work better? Yeah, they would work better if we could make them and have them stay stable in a bottle, but the reality is you make them and they quickly decompose.
Use acid chloride.
And then even beyond that, it's theorized, well, if acid bromides are more reactive, why can't we make acid iodides even? The problem is these are super unstable. So, on your problem of the day over the weekend, I want you guys to think about this because recent research is kind of changing the idea about a lot of these acid halides. And if you do want to look at the primary literature for this, go on the class website on the interesting topics section, and I actually have the literature talking about recent research regarding this. If you open it up, in order to view the full PDF, you have to be on a TCC network, and then you can download and save the PDF. So if you do want to look at it this weekend at home, I would encourage you to download it on campus before you leave school today.
What about acid chloride?
Acid fluorides you don't see.
So
That's a good question. I'm not sure why you don't see them, but they're not useful synthetically.
So the one with the iodine, that's not true.
It's very, very unstable.
So should I cross it out?
I wouldn't cross it out. I'd just say it's very unstable.
But is it more reactive?
Oh, yeah, it's much, much more reactive. All right, I'll see you guys on Monday. Have a good weekend.